Section: Introduction. In this section, we discuss recent advancements in large language models, LLMs, that have shown great promise in expert-level tasks by following user instructions. A key breakthrough is the use of reinforcement learning, RL, particularly methods like PPO and GRPO, to enhance the reasoning abilities of LLMs. Notably, the 0 RL setting introduced by DeepSeek R10 demonstrates that we can train a base LLM directly with RL, unlocking strong reasoning skills without needing supervised fine-tuning. This approach has inspired several open-source projects, such as Simple RL, DAPO, and DeepScale R, which utilize variations of GRPO to improve reasoning performance, either in the 0 RL setting or through continuous reinforcement learning on models that have undergone supervised fine-tuning or distillation. However, most existing methods focus mainly on mathematical reasoning or coding tasks. This limitation arises from two main factors. 1. Data availability. There is a wealth of mathematical data available online from competitions and exams, making it easier to gather large datasets. 2. Answer verification. In mathematics, we can easily verify answers using straightforward methods like exact numeric matching or symbolic equation comparison, which provide reliable reward signals. However, this dependence on rule-based verification restricts the model's ability to generalize. Real-world reasoning often involves various fields, like science, finance, and the humanities, and includes complex answers that cannot be easily verified with simple rules. For instance, while some models improve mathematical performance, they may perform worse in other reasoning areas. To tackle these issues and enhance the applicability of RL-based reasoning models, we propose a new training approach aimed at improving LLM reasoning across various non-mathematical domains while maintaining their mathematical strengths. All-Domain Reasoning Dataset. Web Instruct Verified. A significant challenge in expanding reasoning beyond mathematics is the lack of high-quality, publicly available datasets that cover multiple domains with verifiable answers. To overcome this, we have created a large, diverse dataset by carefully collecting and filtering reasoning questions from web resources, based on Web Instruct. We use advanced LLMs to select questions with reliably verifiable answers, broadening our training to include fields like physics, chemistry, social sciences, and finance. Our dataset consists of around 230,000 high-quality reasoning questions, providing a solid foundation for general reasoning training. All-Domain Answer Verifier. General Verifier. In addition to expanding our dataset, existing rule-based verifiers struggle with the variety of answer types found in broader domains, such as short string answers and structured forms. We introduce a compact generative verifier model, trained to verify short answers in a context-aware manner, which offers reliable reward signals for RL training. This enhances the flexibility and scalability of our RL training across diverse reasoning tasks. Using this diverse and verifiable reasoning data along with our generative verifier, we train a series of general reasoner models in the 0 RL setting from various base models. We validate our approach through extensive evaluations across 12 challenging reasoning benchmarks beyond mathematics, including MMLU Pro and Theorem QA, as well as standard math benchmarks. Our general reasoner typically improves performance on general benchmarks by about 10% and can even slightly outperform math-focused RL frameworks on math tasks, benefiting from cross-domain generalization. Our best model, General Reasoner QW3-14b, matches or exceeds GPT-4o in various benchmarks. In summary, we contribute by creating and releasing a large-scale, high-quality dataset of verifiable reasoning questions with short-form answers across diverse domains, significantly enhancing the resources for general reasoning training. We also introduce a generative model-based verifier for chain-of-thought answer verification, replacing rule-based methods and enabling robust RL training across multiple complex reasoning domains. Our evaluations demonstrate the superior performance and generalization capabilities of General Reasoner in the 0 RL setting, providing a strong baseline for future advancements in RL-driven general reasoning. Section Summary. In this section, we highlight recent advancements in large language models, LLMs, that utilize reinforcement learning, RL, to enhance reasoning capabilities, particularly through the introduction of a new training paradigm that broadens the applicability of LLMs beyond mathematical tasks. We present a large-scale, diverse domain dataset of verifiable reasoning questions and a generative model-based verifier, which together improve the performance and generalization of our general reasoner models across various reasoning benchmarks. Section: Related Works. In this section, we discuss related works on large language models, LLMs, and their reasoning capabilities. We have seen significant advancements in LLMs that allow them to perform various tasks by following user instructions. However, tasks that require expert-level reasoning, like solving complex math problems or tackling practical STEM challenges, demand strong reasoning skills. Recent research on chain-of-thought reasoning has shown that LLMs can improve their performance by clearly outlining their thought processes during inference. Further studies have explored a method called test time scaling to enhance LLM reasoning abilities. Commercial models, such as OpenAI's O1 series, have shown impressive results in reasoning-heavy evaluations, including Math Olympiad problems. Additionally, open-source models like Qwen, QWQ, and DeepSeek R1 have also achieved competitive results, closing the gap with top commercial models. This progress encourages academic exploration of advanced strategies to further boost LLM reasoning capabilities. We also explore a method known as zero reinforcement learning, RL, for LLMs. Typically, enhancing reasoning capabilities involves supervised fine-tuning with chain-of-thought data followed by reinforcement learning. However, studies like DeepSeek R10 have shown that we can apply reinforcement learning directly to a strong base model to reveal significant reasoning abilities without prior fine-tuning. This zero RL approach has gained attention in the research community, prompting efforts to replicate and improve it on other powerful models like Qwen. One major benefit of zero RL is its efficiency in gathering verifiable question-answer pairs, which means we don't need complete reasoning chains as training targets. This allows for more flexible improvements in reasoning performance without complex data collection, enabling models to enhance themselves more effectively. However, most existing work on zero RL has focused on mathematical reasoning. While other projects like CrossThink and RLVR aim to broaden reasoning capabilities, we focus on using a model-based verifier to scale diverse reasoning data across different domains and provide thorough evaluations of effectiveness. To support strong reasoning skills across various domains beyond math, we have created a large-scale, diverse, and high-quality dataset of verifiable reasoning tasks. Our dataset building process starts with the WebInstruct dataset, which contains around 5 million web-crawled instructions from reputable sources like Stack Exchange and educational websites. Although WebInstruct is suitable for general instruction tuning, many documents lack clear verifiable answers or require reasoning processes. To tackle this, we trace entries back to their original web pages to collect precise question-answer pairs, filtering out questions without identifiable human-written answers. We also exclude questions from sites that require membership or complex interactions to access answers, ensuring that the remaining entries are verified by humans for reliability. Next, we utilize Gemini 1.5 Pro, a state-of-the-art LLM, to extract questions that have clear verifiable short answers. This results in an intermediate dataset of about 1 million verifiable reasoning questions across various fields. We then use Gemini 2.0 Flash to annotate each question with metadata, such as answer type, subject category, and difficulty level. To balance the dataset, we filter out math problems labeled as easier than university level. Acknowledging that web-crawled data can be noisy, we implement strict filtering to enhance dataset quality. Specifically, Gemini 2.0 Flash generates 8 candidate solutions for each question, allowing us to apply quality control criteria. We exclude questions where all candidate solutions fail, removing ambiguous or noisy questions, and also filter out overly simple questions where all solutions are correct, ensuring the dataset remains challenging. Ultimately, Our processed dataset contains around 230,000 reasoning questions across various answer formats, including multiple choice and numerical expressions. We illustrate the balanced domain distribution of our curated dataset, which covers subjects like mathematics, physics, chemistry, finance, and various humanities and social sciences. This thorough data curation process results in a challenging yet reliable dataset for training generalizable reasoning capabilities in large language models. Section Summary. In this section, we discuss advancements in large language models, LLMs, for reasoning tasks, highlighting the effectiveness of chain-of-thought reasoning and the emerging zero-reinforcement learning approach that enhances reasoning capabilities without prior supervised fine-tuning. We also outline our process for creating a diverse and high-quality dataset of approximately 230,000 verifiable reasoning questions across various domains, ensuring robust training for LLMs to improve their reasoning performance. Section Preliminary. In this section, we adopt Group Relative Policy Optimization, GRPO, building on recent advancements like DeepSeek R1. For each question-answer pair, our behavior policy samples a group of individual responses. The GRPO objective helps us update our model parameters. Our model-based verifier specifically influences how we compute rewards. We identify limitations in existing reward models, which typically rely on human feedback to return scalar values that indicate overall quality. While this approach seems straightforward, it can be manipulated by the policy model and often requires a large parameter size to be effective. In contrast, rule-based verifiers, commonly used in mathematical reasoning, evaluate only the final answer, allowing for more exploration of diverse reasoning paths. However, these rule-based methods have significant limitations when applied beyond mathematics. They often require exact matches, fail to recognize semantically equivalent answers, struggle with varying answer formats, and have difficulty adapting to different disciplines. For training, we utilize a 0RL setting, performing reinforcement learning directly from base large language models without intermediate supervised fine-tuning. We initialize our models using the Qwen 2.5 and Qwen 3 families and apply the GRPO algorithm. We choose the general Qwen model to enhance overall performance, even if it may lead to lower scores on mathematical benchmarks. During training, we assign reward scores based on solution extraction success, applying penalties for excessively long answers. Our training occurs on multiple nodes with GPUs, with the average response length increasing from about 700 to 1,000 tokens over approximately 2 to 4 days. To evaluate our model's reasoning capabilities, we conduct assessments across various challenging benchmarks, including MMLU Pro, Super GPQA, BBEH, GPQA, Theorem QA, and several math-related tasks. We use a specific evaluation framework and check answer equivalence with GPT-4o. Our main baselines include the Qwen 2.5 and Qwen 3 families, Simple RL, Open Reasoner 0, and Nemotron CrossThink. The results show that our general reasoner consistently outperforms both base and supervised fine-tuned models across various benchmarks. For instance, with the Qwen 2.5-7b base model, we achieve 58.9% on MMLU Pro, surpassing the base and instructed models. Similar improvements are noted with the 14b backbone, and we see strong performance on math-related benchmarks as well. When initializing with Qwen 3, we observe even better results, demonstrating the efficiency of our training method. The best-performing version, General Reasoner QW3 to 14b, matches or exceeds the performance of commercial models like GPT-4o, despite relying solely on 0RL. While there are still performance gaps compared to closed-source models, our findings highlight the potential of zero-reinforcement learning combined with diverse reasoning data and a compact verifier. Importantly, our model does not exhibit overthinking, maintaining shorter response lengths compared to other methods, and achieving higher accuracy in significantly less time. Section Summary. In this section, we adopt Group Relative Policy Optimization, GRPO, to enhance our model-based verifier, addressing limitations of traditional reward models by allowing more flexible evaluation of answers. Our training, conducted without intermediate fine-tuning, demonstrates that our general reasoner consistently outperforms existing models across various reasoning benchmarks, showcasing the effectiveness of zero reinforcement learning combined with diverse reasoning data. Section: Impact of Data Abundance. In this section, we examine how the variety of training data influences reasoning performance. We compare two versions of our zero-RL setup, one trained on a comprehensive, diverse dataset and another focused solely on math-related questions. Our findings, presented in the table, show that for the 7B backbone, training only on math tasks results in a slight improvement on the math-related benchmark, but it negatively impacts general reasoning, with drops in performance on other benchmarks by about 2 percentage points. Conversely, the model trained on the full dataset performs better overall, showcasing enhanced general reasoning skills. The 14B backbone shows an even more significant advantage from diverse data, outperforming the math-only model across all metrics. Next, we explore the impact of our model-based verifier on training. We conducted an ablation study comparing models trained with our verifier versus a traditional rule-based verifier, both using the Quen 3-4B base model under the same conditions for 120 steps. The results indicate that the model-based verifier leads to higher accuracy across all benchmarks. We noticed that the rule-based verifier plateaus around step 60, while the model-based verifier continues to improve, reaching about 60% accuracy by step 120. This suggests that our verifier effectively enhances reinforcement learning, allowing the model to utilize diverse training data more effectively. Lastly, we assess the agreement of our model-based verifier with Gemini 2.0 Flash. We found that the rule-based verifier has a high false negative rate, achieving only 22.2% agreement on average with 50,000 answer verification pairs deemed correct by Gemini, while our model-based verifier reached 78.7%. We analyzed agreement across different answer types and found that false negatives are more common in unstructured formats like lists or strings. Even in structured formats, variations in how answers are presented can lead to discrepancies. Our analysis also shows that the model-based verifier is particularly effective in non-math STEM fields, such as physics and engineering, where answer formats vary widely, while fields like economics, which use more structured answers, show a smaller performance gap between the two verifiers.